Okay, good morning. Thank you very much. And I would like to thank the organizers for the invitation to participate in this conference and to give a talk. Naively, it may look like that the only relevant word is higher in the title, but I will try to convince you that that is not, it's more than that. And the higher actually is very much related to the higher structure that I discussed in this conference. Okay, so my plan is that I will spend most of my time on some general introduction to what is known in this field. The field is very large, actually, and I will not be able to discuss all aspects of it, but I will try to emphasize some features that are, I find, most relevant to what people are considering here and actually what I'm doing. And then in the end, if I have time, I hope to have it, I will explain some very recent results, actually like 4 months old, on the new extended construction that may help us to understand how to relate these higher string theories with string theory and actually M theory in the end of the day. So there is a hope that this may be a shortcut allowing us to reach the goal that was estimated to be reachable in 300 years a couple of days ago. So, okay, so to begin with, let me explain the main motivation for this study. So the main motivation is quantum gravity challenge, which I don't think is available, even though the string theory is the best candidate for describing quantum gravity these days. And the point is that the scale of energies that is typical for a quantum gravity regime is this Planck scale, which is extremely tight and compared to available energies, at least Earth experiments. Well, some people say, why should we care? It's so much far away from what we can actually test. But you never know in physics what will happen, and there is a standard textbook example of special relativity that naively would never help to understand anything for everyday life speeds. But because of this formula, it turned out just opposite. It's just actually most of physics, and even biology, by the way, is based on special relativity. I mean Darwin theory, because it has differences, difficulties, as maybe you know that there was not enough time for developing it, actually, unless people realize that there is radioactivity. All right, so the main motivation is just to try to understand this, but because the energies are that enormously high, we should somehow rely on some general principles, and there is a very simple idea that we may conjecture that at so high energies, some higher symmetries may show up, pretty much like in vector weak theory, for instance, about the scale. So then the idea is that why don't we try to understand what kind of higher symmetries can be introduced in relativistic field theory and to see the consequences. And then it turns out that actually this conjecture is extremely restrictive and leads to a very specific and very concrete set of theories. This is what I'm going to tell you about, and this is what the word gauge is most important, because gauge theories means symmetries. So we'll see that in some sense these are theories exhibiting maximal symmetries. I will explain later on what does it mean, which go beyond the standard list of symmetries and supersymmetries which are normally considered in the QFT. So that is the main idea. So the starting point for many in this field is the so-called Franzel theory. Franzel in 1978 formulated at the free field level theory of massless fields of any speed s in 4 dimensions. So he has shown that they can be described by symmetric tensors of rank s, which are subjected to some by some double bracelets conditions, never mind. But the point is that these theories, pretty much as spin 1 and spin 2, are all gauge theories, with the gauge parameters being rank s minus 1 symmetric traceless tensors. So, well, actually, particular examples were available before that, but Franzl considered the problem in the generality and found this very uniform description for free massless fields, which were all gauge fields. So he found action and he found equations of motion, of course. I'm not giving action, but the equation of motion can be put into this very simple form where G is an analog of the Einstein tensor in gravity. So this operator, second order, is indeed gauging variant under these gauge transformations, and this is what fixes this operator up to a general overall constant. So this is the starting point. So the idea was that, and actually this is what Franzl already formulated clearly, that we should somehow go to interacting theory starting from this. But then it was not so obvious how to do that, because even before Franzl, there were works, fundamental works by Weinberg and Coleman and Mantova, where actually it was argued that it is not possible to have a theory exhibiting symmetries beyond the standard list of low energy symmetries in Minkowski space. So that was the very strong and correct statement. And that's why people were confused, and in those days people basically were claiming that no Hairston, non-trivial Hairston gauge theories can exist. Well, then on the top of that, in 70s, Aragon and Deser considered what would happen if one would switch gravitational interaction to the spin 5-half. They considered specifically, and they found that either diffeomorphisms or gauge symmetries for Hairston fields, but not together. I mean, that was another no-go statement. So it turned out that the way out is to modify slightly the conditions of these no-go theorems by going from flat Minkowski space to ADS background with non-zero cosmological constant. It was realized in '87 that this works. All this story actually is related to supergravity development, and actually Franzl, as you can notice, developed his theory after supergravity was already discovered. So there is a similar phenomenon in the gauge supergravity where if one wants to have charged gravitinas, then cosmological constant shouldn't necessarily be non-zero. And that was a kind of, useful observation from that perspective. So ADS is, as you know, is a curved hyperboloid with a radius r squared related to cosmological constant up to some coefficients like pi and so on and so forth. Okay, so those days the ADS CFT correspondence was not around, and it was considered as some strange peculiarity of these theories that anti-de Sitter background plays an important role. I will try to explain actually how it works in practice, how ADS background works, helping to resolve the original problems. But even though it was clear, let me emphasize this from the very beginning, that when one says that Hairston theory is formulated in ADS background, this is related to the phase where all Hairston symmetries are unbroken. That is, I mean, has nothing to do with the consequences of these theories once Hairston symmetries are broken, which may have a result of giving masses to Hairston fields and shifting a vacuum energy, which means shifting cosmological constant. So this is about most symmetric phase. All right. So, but after ADS CFT correspondence came in, well, Klebanov and Polyakov actually made a conjecture on the possible ADS CFT dual for Hairston theories in 2002. And they conjectured that the Hairston theory that I'm going to explain to you in more detail later on is related to the three-dimensional vectorial conformal sigma models, either for bosons or for Fermions. Well, they specifically considered bosonic case. Fermions were considered by other people like Petko, and there was several works actually on that. Okay, so then it took another 7 years to check this conjecture, and it was checked by Durham in 2009. That resulted in some very larger increasing activity in this field, and moreover, that's already gave an example of an unexpected prediction of the theory of high-spin fields, because somewhat later this conjecture was generalized by Aronian, Minwala, and the collaborators to somewhat more general conformal models at the boundary that are Chern-Simons conformal models, either for bosons or for fermions. And there is a new constant in this case, which is the level of Chern-Simons. And it was conjectured that this level, this constant, is related to a particular coupling constant in the framework of high-spin theory that I will show you later. And there was an unexpected prediction that somehow playing with this freedom with the coupling constant, looking from the bulk side, the prediction was that there is some duality between bosonic and fermionic models of this type at the boundary, and that has been checked. That was actually a rather actively developing issue in this study of this model, and it is called sometimes three-dimensional bosonization. So that was a rather non-trivial relation between interacting theories in 2+1, not in 1+1. All right. So then the correspondence was extended by Gabriel and Gopakova to ideas 362, and one of the motivations was that because this kind of model is much simpler than chemical force over Young-Mills and string theory, then maybe it will help to analyze and to understand the origin of ADS-CFT. Okay. Any questions so far? Good. So now I'm going to explain you what is the simplest example of the high-spin symmetry. Originally it was found directly from the analysis of the high-spin gauge theory in 4 dimensions. But then after ADS-CFT correspondence came in, we realized that what is ADS symmetry in the bulk is the same time conformal symmetry at the boundary, and the conformalization is sometimes simpler. So I will use this boundary language to derive this symmetry, to explain you what it is. So usual conformal symmetry in D dimensions is OD, and from the ADS D+1 perspective, this is just the ADS D+1 symmetry. So now let me start with the three-dimensional model, which is a kind of boundary for the ADS4. And let me analyze the simplest possible equation that is available, which is free Klein-Gordon. So because it's free, it has infinite dimensional symmetries. And the question is what they are. Well, it's not that completely simple a question. I mean, if I would try to find it by brutal force, it will take some efforts to derive. So in the end, mathematically, one can describe it as some quotient in terms of modules. I will give an explicit construction for the 2001, following to my paper with Schenkman from 2001, where actually the result is very simply formulated and actually gives hints what to do next. So let me explain you how it works. First, I will consider the language of two-component spinors. So in 2+1 dimension, spinors have two components that are real. And the most important point is that there are exactly 3 symmetric real matrices, 2 by 2. And this can be identified with the space-time coordinates x using the tau matrices of this type, which are real 2 by 2 matrices. Well, the construction is Lorentz covariant because the determinant of this x is precisely the 2+1 dimensional interval, so that this is just the language which makes the SP2 language explicit instead of O21 language, which is typical for the standard vectorial formulation. All right, so far so good. So we will use this notation for derivatives, which is ddx alpha beta. And now let me do some procedure which actually is very closely, I will show you later on, is actually the first step towards infinity, and actually I don't think algebraic construction in this field, but let me just do it directly. So we want to describe equations for a scalar, okay? Let us just consider first derivative of a scalar. And there are no restrictions on the first derivatives by Klein-Gordon, so we just call this derivative by a new letter, C alpha beta, introducing a new field. So it's unrestricted. But then we can continue applying another derivative to the new introduced field. And this will give us some guy that is symmetric in alpha beta, symmetric in gamma delta, actually symmetric under exchange swapping of these two pairs, but that's it. Then one can observe that if one wants Klein-Gordon equation be true, then it imposes this condition, which is equivalent to the condition that this guy should be totally symmetric in all alpha beta gamma delta. Okay? So that is what imposes Klein-Gordon equation in this language. So okay, we want to be on shell, so we demand this guy be totally symmetric, and then we can continue analyzing higher and higher derivatives, and we'll find that the full set of higher derivatives of the original field C on shell, when the Klein-Gordon equation holds, actually is determined by this equation that should be read from the right to the left. So this is the definition of higher components in terms of space-time derivative of the lower ones. And the meaning of this equation is that all these higher components parameterize all on-shell non-trivial derivatives of the original field. Well, it has another interpretation in terms of modules. This is actually, that's components that do form a modulo of the three-dimensional conformal algebra, and actually the original field is just a primary field, and all others are descendants. So that actually expresses the whole story in terms of representations. I will come to that later. But now it's extremely simple to find the symmetries. Let us organize all these components into a single generating function by introducing additional spinor commuting variables y. So all this bunch of higher and higher tensors are now described by a single function of x and y. And those equations that we have been wrote in terms of components now can be reformulated in this very complex form. So we see that ddx is the same as ddy ddy, and Klein-Gordon just results from this representation that these components are symmetric. Okay, but for this equation, to find the symmetry algebra is an elementary exercise. It's just nothing to do. Just observe that. We will see that this is a covariant constancy condition, of course, later on, but it's so simple that we may even don't use this. So basically, consider variation like that with epsilon that depends on y, dy, and x. And then we can see that the equation becomes invariant, remains invariant under the transformations where three parameters in these transformations are given by an arbitrary function of y and dy. So here is the g minus 1 g factor that removes actually this second term that makes the connection trivial. So this is how the symmetry transformations do act on the solutions of free Klein-Gordon equation in 2+1 dimension. And after all, they are not that simple. I mean, if you will try to find somehow some higher spin transformation, higher spin means higher polynomial components of these global symmetry parameters, that will be messy if you don't know this part and don't know how this ddy dy are related to ddx. But once we know this, this is very simple, and most importantly, we know what is the algebra of this series. We realize that the symmetry is given in terms of arbitrary parameters, which are arbitrary functions of y and dy. So this algebra is, of course, very well known. This is Weil algebra. So this is the algebra of differential operators with polynomial coefficients. So this is a very nice object in math, and this is what happens to be the simplest Hierstein algebra in this conformal setup at 2+1 dimension. So we know what it is. As I said, originally it was found different by different arguments, a lot more complicated from the box side, but it is the same algebra because, after all, now I understand that it should be the same. So, yes, please.
So it looks like this unfolding trick amounts to exchanging the equation of motion with the constraint, in a sense, right?
Yes, probably you're right. I mean, what does it mean, constraint? Constraint in terms of, yeah, you mean the constraint on the y.
Which have constraints,
right?
Yeah.
Exactly. Yeah.
So is it always the case?
Sorry?
Is it particular to this problem, or is it always the case that unfolding can be solved?
Well, if yeah, it's always the case. I mean, it depends, of course, in which terms do we do this. I mean, here we have introduced a particular class of y functions of y, and that is the constraint. So these functions, they are free. I mean, and the functions of y are not restricted. The constraint is that the whole story reduces the functions of y. Okay, so this is similar. In fact, it's basically is the kind of Twister transform. You say that you go to some other space of y variables here, and every function there generates the solution of your equations in the original space-time. So this is the game, how it works. But, I mean, this example is most simple in the sense that the twistor part is very simple. It's just actually just plain, actually, in this example of y. But in many other cases, it's not that simple at all. So it should define somehow properly the corresponding analogous space in the, well, fibers in certain description. And that's why actually similar construction in arbitrary dimension, it exists due to Eastwood, but it's a lot more involved in practice. So as we are used to, the special dimensions where twisters show up actually are indeed special and simplify the life a lot. So this is one of the cases. This is not, by the way, not twister in the standard mathematical sense in terms of some parabolic spaces. Because, you know, this operator is second order. And normally, I mean, in the twistor geometry, one considers vector fields, which should be first order. That is achieved by partial Fourier transform in 4 dimensions when we have y bar, and that's what gives you twistor theory. But this day, at least after Wittenberg 10 years ago, reformulated it as second order operators, people are used to, I mean, in physics at least. And when I talked to Eastwood saying something like this once, he was pretty much surprised with what I mean, actually, because this is not quite exactly the twistor picture from the mathematical point of view. It's not a vector field. All right. Any other questions? Okay, let me just summarize properties of these algebras, because a lot follows immediately from this construction. So, spin is related to degree of a polynomial in y and y bar, or a y and ddy in this setup. The algebra is not commutative, but then one should be careful by saying the degree of a polynomial in which particular basis one works. Here, in most cases, I will be using the Weil ordering, which is totally symmetric. Then if one would compute 2 generators of spin S1 and S2, I will get the standard spin rule that the generators will go from the sum -2 to difference +2. All right. So, and the point is that once there is any spin exceeding 2, then commuting these generators will be giving you a higher spin. So starting with spin 3, for instance, commuting spin 3 to spin 3, one will get spin 4, so on and so forth. So the point is that spin 2 is a barrier after which the algebra symmetry algebra becomes infinite dimensional. And spin 2 is given by bilinear polynomials, which of course commute to themselves. This is just the SP4 algebra, subalgebra of the wild algebra. And this is at the same time ADS4 algebra and CFT3. Well, there is also central elements that actually is related to inner symmetries, and there are some series of matrices, of matrix-valued algebras of these types. I will skip this just due to the lack of time.
So the TS are the generators of the higher spin algebra?
Yes. Yeah. And so we see that if we go beyond the spin 2, then actually we will need to introduce infinite number of them, just looking at this simple example. This is what happens in any theory of interacting, propagating high-spin fields. Okay, but moreover, from what we have considered, it follows that something dramatic happens to the space-time picture where these fields do live. Well, first of all, our high-spin generators, they carry spinor indices, which means that they carry tensor indices equivalently in the vectorial language, tensorial language. And that has a simple consequence, that the Lorentz generator commuting to higher-spin generator gives a higher-spin generator. And actually, in ADS, or in conformal setup, other generators also have the same property. They map higher-spin generators to higher-spin generators. Well, this is a trivial way to understand these relations, but there is another one. Why don't we interpret them differently? That we apply higher-spin transformation to space-time symmetries. If we apply higher-spin transformation to space-time symmetries, we will get a higher-spin transformation. And that has immediately a consequence that our gauge fields associated with space-time symmetries. Let me remind you that these are fields of conformulation of gravity, but metric tensor in particular, are not invariant under the higher-spin gauge transformation. So if we apply a higher-spin transformation to metric tensor, we will get a higher-spin field. But that is simple but very important consequence. This means that basically we can't use the language of Riemannian geometry in this setup. It's just not invariant. And this means also that once the notion of metric is not invariant, then this means that our theory has a good chance to become non-local in some sense, in one sense or another, because metric is what measures the distance between the two nearby points. And this is not invariant anymore. So we may have difficulties with measuring, saying that 2 points are close or not. So we should be prepared at least to this. And this is not that much surprising, because let me remind you, in the beginning of my talk, I was arguing that we are talking about so high symmetries that they show up at the Planck energies and beyond. And actually, we should not expect that the quantum gravity theory is a standard local quantum field theory with two derivatives. At least we should be prepared to some new terms going into this regime. So this is how it's, well, not slowly actually, very quickly happens. Okay, so Riemannian geometry can be used, but it's just inconvenient because it's not covariant under higher spin symmetry, in the sense that spin 2 gauge field is mapped to something else, to higher spin gauge fields. On the other hand, of course, talking about some gravity theory, it's important to have diffeomorphisms. And fortunately, there is a way how one can do this. This is to use Cartan formalism of differential forms. And elaboration of this language actually leads to very interesting and important consequences as well. And the first one is that the way how one can formulate dynamics of these fields in terms of differential forms actually immediately leads to L infinity and essentially A infinity structure behind higher spin theories. This is what I'm going to explain now. So this is what is called, indeed, in the literature, unfolded dynamics. So let me say a few words about it, because, as I said, the structures are absolutely relevant to the main topics of this conference. Well, the idea is very simple. An example I have already given when I was working with the massless scalar in 2+1 dimension. So, well, we all know that it's sometimes very useful to reformulate ordinary differential equations in the first order form. This can be easily done by simply denoting by a new letter every derivative of our dynamical field that is not determined by the field equations. So let us try to do something similar, but now with respect to the differential rather than just ddt. So to this end, we have to replace our variables q in the ordinary differential equation theory by a set of differential forms, whatever it is. And then we can try to reformulate our dynamical equations in this form, that the ramp applied to every field is some function of the same set of fields. So, well, this function g is a function of w, it's not of x. One can also introduce the exponent, but it's not necessary, and actually is not needed in most of the cases. So, so it's some power series expansion. And to guarantee that these equations are formally consistent with the condition that d squares to 0, one should impose these Jacobi-like conditions on the function g. Well, this construction actually was known in physics after the papers by Freya, Uriah, Peter von Nieuwenhuizen as pre-differential algebras, and well, originally appeared in the paper by Sullivan, I think. But in all those cases, Sullivan, actually I was asking him personally, and he confirmed, and Uriah and Freya. So these were indeed normal L-infinity algebras in the sense that they were not considering zero forms in the construction. Here, in what I'm proposing here, zero forms actually do play a fundamental role. This is where non-trivial dynamics is concentrated, and that's why what we are talking about is kind of L-infinite algebra. And let me explain how it works. So originally I didn't use these words because I think that these words were not around in those days. Okay, so there is an important particular class of systems which we call universal, and these are the systems insensitive to the dimension of space-time where the round differential is defined, in the sense that it does not use the fact that some form is maximal. So we don't use that some form of degree d+1 is that any form of degree d+1 is 0. So if in this case the system is consistent, then one can define the Q operator such that it squares to 0, and this is the form of unfolded equations for all those systems, and this becomes a Q-manifold. With the target space having coordinates W, and the original space being our original space-time, so this is like some presentative condition that have been discussed many times at this conference, I think. So this is a general form for unfolded equations, and all those equations that are available in higher spin theories belong to this universal class. So they belong to this Q-manifold construction. Well, in that case, the equations are invariant under these gauge transformations, and this is 100% important for the analysis of higher spin theories because the main feature that we have to care about is precisely the higher spin gauge symbol. I'll come to that. Okay, any questions so far?
So yeah, just the usual. So wait,
Just
so what's big F, what's the little?
Sorry?
What is capital F and little?
F is any function. Oh, this is just a type of thing. So they are the same.
So it's
Sorry. Yeah.
GF equals UF.
Yeah, it's like in Hamiltonian dynamics. You can apply to every function your construction. Yes. Thank you. That's
So the equation basically means the equation basically means that we have a morphism from pi Cm your M space-time to some Q manifold, right?
Yes. Yeah. But these are equations.
Yes.
These are dynamical equations. I mean, this morphism means implies dynamical
Yes, of
equations.
course. So the condition that is Q morphism, it's an equation.
Yeah,
Obviously. So-
right. And actually, I gave already an example. When I was doing this story about free fields in 2+1 dimension, I actually reformulated it in this form.
Q is generated,
Q is just, well, it's just homological vector field in this Q manifold. Yeah. All right. Now I will repeat some couple of features that actually have been discussed many times. So, how to interpret these equations perturbatively, where the perturbation theory exists. First, the vacuum solution to these equations is normally given by some flat connection. So if you consider G of omega, omega is a particular part of this W that is restricted to something smaller. So if there is a Lie algebra, then one can consider one forms associated with this Lie algebra, and then G of omega can be chosen in this form, so that one is left with the Maurer-Cartan type equation, which of course is consistent, and in that sense, in that case, the continuity condition is just Jacobi identity for some Lie algebra H. And this is the Lie algebra underlying the L infinity structure. I will not, in many cases, make difference between L infinity and L infinity algebra for just simplicity. Okay, so this is what describes space-time geometry in this language. It is very well known that de Sitter, Minkowski, conformal group, they can all be described by this simple equation for the appropriate symmetry algebra, which is conformal algebra or de Sitter or Poincare. So the advantage is that this formulation is actually coordinate independent, so one should not specify even this flat connection, whatever it is. Well, there is an additional condition that the frame-like component of this connection should be non-degenerate to have metric tensor non-degenerate if we want to describe our space in standard sense. All right. So then one can consider fluctuations, consider deviations from the background, well, interpreting them as small, and then what will result is that this deviation will be satisfying some equation like this, which is maybe dependent on the background field, but should be linear in the field's fluctuations themselves. And then the probability condition is just that this C is valued in the some H module, where H was the module where the connection was taking its values. So we see that at this level, free field or free dynamics is described in terms of just directly H modules. This has many consequences. By the way, the example that I was considering, I just reproduced the same equation, was precisely of that type, because that can be interpreted as translation generators in the Y space for the Poincare algebra in 2+1 dimension. So we precisely formulated in this way the 2+1 dimensional scalar field. And this is the simplest possible example. It is a zero form, and that's why zero form play an important role in the construction. And that is a very general story. Okay. By the way, these modules that appear in this setup, they are not so much unusual from the field theory perspective. This is almost the same as the space of single particle states in quantum field theory. So if you consider space of single particle states in quantum field theory, they of course form modules of the space-time symmetries you work with. The difference is that in quantum field theory, these modules are unitary, and this is not, because here is the where the Lorentz symmetry is realized by finite dimensional representations. Lorentz is not common. But basically, they are related by some kind of complex equivalence relations. So they are not unitary equivalent, but they are equivalent by some non-unitary map. So this, again, this story is pretty much is not that unusual, and moreover very useful, because if one would be interested if one or another model is unitary or not, then one can analyze this in terms of modules by just checking whether or not this module has unitarization. And this in particular does have its Fock space in the Y readiness. Okay, let me summarize some properties. Well, actually, this discussing properties of this formulation can take a lot more time than I have. So, number one is that this formalism is actually general. One can apply it to any dynamical systems, and everyone may think that, okay, that diffeomorphisms may not be available in every system, but in fact they formulating background in diffeomorphisms in variant way allows you to proceed even for in the Minkowski space the same way. So, most important for the analysis of high-spin gauge theories is that gauge symmetries are manifest. So, given the unfolded formulation, there is a prescription how to write down gauge symmetries so that every form of rank 1 in fact has a symmetry parameter which is arbitrary function of x of degree p minus 1. That is precisely what actually the main goal for analyzing high-spin gauge symmetries is about that. I will come back to this point in a few slides. Of course, the diffeomorphisms are built there. What is about interactions? Interactions is a deformation of this function g, or a deformation of this homological field in the Q-manifold interpretation. Where are local degrees of freedom? This is important. So, local degrees of freedom, this is a local statement. If there are non-trivial boundary conditions or non-trivial topology, then of course it goes beyond that. But local degrees of freedom can only sit in the zero forms. This is roughly the usual Poincare lemma that tells us that only zero forms may have non-trivial homology. So basically, not what describes dynamics should sit here, and this immediately implies that there should be infinite number of zero forms to describe some non-trivial field theoretical model. And this is what we have seen already, because our zero form in the example of 2 plus 1 dimensional model was given by functions of y. So fixing some x, we still have infinitely many degrees of freedom, and this is a substitute for the standard Cauchy problem in the differential equation theory. Okay, so from the Lie algebra interpretation, this is the story about Chevalier-Lindbergh homology, or Hochschild homology in the A-infinity case. And basically, this is also something that have been discussed at this conference many times. But here is important additional moment. The models we are considering, they are working with infinite dimensional modules of our H symmetry. And that is what allows us to have non-trivial concycles of this type. And this is what indeed appears in the construction. I'll show you examples. So there is a non-trivial Chevalier-Lindbergh homology with coefficients in the infinite dimensional modules. This is how it works. So that is important, that there are zero forms, number one, and these zero forms span infinite dimensional modules.
So in contrast with Whitehead lemmas with prohibit homology in finite dimension.
Absolutely. So it works very consistently with that, yeah. It should, of course. All right. And somewhat unexpected feature that was not immediately realized is that somehow after equations are reformulated in this way, and after it is shown that the corresponding system is universal, then actually the original space-time we started with somehow not disappears, but it becomes a secondary concept. The whole story is entirely encoded in this homological field in the target space. Let me explain you a little bit about this, because in fact the consequence is that to some extent different homological fields in this population define classes of holographically dual models. So let me explain how it works. It's a little bit naive statement, and again it's a very local statement, but still I believe it's important, and you have examples and you can check this. So that is extremely simple. It's, okay, so well, actually, unfold applications, they are useful to exhibiting various types of dualities. So there are dualities in the same space that depends on the prescription that I had no time to explain how to define what are dynamical fields, what are auxiliary fields. So there is an issue of this, and there is certain homology responsible for that. But let us focus on the holographic duality between theories in different dimensions. So what I'm saying is that if the system is universal, one can play a game by extending space, considering pullbacks or push forward to some other space. And then the system still will be formally consistent, and one can try to analyze what is described in one space, what is described in the other. Of course, if just adding more coordinates without changing anything, it's a kind of trivial, because basically this equation will tell you that there is no essential dependence on the additional coordinates, so it's not very interesting case. The case becomes interesting when there is a possibility to introduce a non-trivial flat connection with respect to a larger symmetry algebra having components in these additional directions. And this is precisely the story about ADS-CFT. So we can consider conformal connection for the conformal group that is has components in the boundary space, but then we can extend it to a connection of ADS algebra in ADS space. And once we do that, then this extension becomes kind of non-trivial. Moreover, in the examples that have been checked, one can see that that precisely, at least kinematically, responds to standard correspondence between bulk and boundary theory, in particular in the Gribanov-Polyakov case. If we consider a theory in the bulk, we have all massless fields. If we consider a theory at the boundary, we have all conserved currents at the boundary. And the same unfolded equations will give you conservation conditions plus nonlinear corrections. Okay. So that's basically allows us to conjecture that there is a way to identify holographically dual models. As I said, this conjecture is extremely oversimplified in the sense that what I said assumes that topology is trivial. If topology is not trivial, then of course things will be, let's say, more interesting. Okay. Let me move on. So now I would like to say a few words of the original higher spin theory, going to the nonlinear description. But first, let me very briefly summarize how the higher spin fields are described at the free field level of this language. So the description is very much similar to the description that I derived for you in 2+1 dimension, but now we are in 3+1 dimension and in the bulk picture with ADS. So again, we have y and y bar instead of ddy as in 2+1 dimension. So algebra is the same, which means that our 1/4 omega, they are valued in the Weil algebra. And I will show how the Weil algebra structure appears soon. So basically we introduce 1/4 omega, depending on this function of this coordinates y by bar, and also introduce some 0/4 y by bar. There is a label I that plays a role. Actually, when the labels are equal, then the modules of anti-de Sitter algebra are finite dimensional. When they are different, then they are infinite dimensional. That is shown by the formula here. But let me just give you that, tell you that free field equations for all massless fields in 3+1 dimension, in flat space or ADS, that matter so much, they can be nicely formulated at this point. So R1 is a linearized higher-spin curvature for the Weyl algebra in the background, so that it has this very simple form. So it's joint covariant derivative, joint with respect to the Weyl algebra, acting on the one forms. And it has this first order form, very simple. dl is the Lorentz covariant derivative in the terms of spinors. So this is the first order differential operator in y variables. Okay. This is how the R1 is defined. And d tilde is again a covariant derivative, similar to the covariant derivative that we have seen already in 2 plus 1 dimension. And now it's given by this operator, and now it's invented de Sitter, and this operator is also second order. To go to the Twister language, one can consider half Fourier transform with respect to y bar or y. But most naturally, from that perspective, this is second order. Okay, so what happens here? If we had zeros here, then this would mean that there are no degrees of freedom in the fields described by one forms, and this is dynamically trivial situation, not interesting. To make higher spin fields propagating, one should say that some of the components of these curvatures are non-zero. And here are the components. So these are terms which are not demanded to be zero by field equations, and which remain free. And this is from where this module of C fields start. These are, again, primary components of this module. So what is the meaning? The meaning is that these C0 forms actually are very well known for lower spins. For spin 1, this is just a Faraday tensor. This is equation like dA equals to C. This is the Faraday tensor appears on the right-hand side. There are no conditions by Maxwell equations on the Maxwell tensor. There are conditions on the derivative of the Maxwell tensor. For spin 2, this equation tells us that the linearized part of the Riemann tensor, which is given by this formula, is non-zero for those components of the Riemann tensor that belong to the Weyl tensor. So which essentially is equivalent to saying that Einstein equations are imposed, which means that Ricci tensor is zero, but everything else is not necessarily zero. So this is everything else. This is the Weyl tensor that appears here. So from the unfolded perspective, so this becomes a kind of first step towards the full formulation where this actually Chevalier and Beck homology of that de Sitter algebra shows up. And this module is infinite dimensional. That's what allows it to be non-zero. So that's what allows to be non-trivial the higher spin field equations. Okay. And now we want to understand how to deform these equations to interact with the interacting case. Okay. So what are the conditions, what we want to have? We want basically two properties. We want that in the free field limit, this theory should, whatever it is, should reproduce the original frontal theory, or equivalently, in the unfolded language, it should reproduce these equations marked by stars. And another property is that there should be non-abelian higher spin gauge symmetries in this theory, because relaxing this property is very easy to construct interactions just by adding some terms built out of the abelian curvatures for higher spin fields. So the condition is that they should not be abelian, that the symmetry should be formed. In fact, it necessarily will be deformed because we insist on having diffeomorphisms already there, which is a non-abelian structure. So the same conditions for spin 1 and spin 2 leads to fundamental models like Young-Mills and Einstein theory. So let's see what will happen for higher spins. So as I said, I would like to explain why de Sitter plays so important role. This is a very old story, like 30 years old. But, I mean, maybe it is useful to understand how it works, because naively one may think that it is a kind of triviality. like dividing over the curvature. It's not like that. So the problem that I have mentioned already due to Argon and Desert was that they started with the frontal theory, covariantized derivatives, and now observe that because covariant derivatives do not commute, they commute the Riemann tensor, then the variation of the gauge variation of the original action becomes non-zero when R is non-zero. And the essential point here is that for lower spins like spin 3/2, for instance, on the Ricci tensor appears here. Simply there is no room for constructing indices for the wild tensor in that case. And that's what allows to construct supergravity, because the all terms proportional to Ricci tensor can be compensated by the modification of supersymmetry transformation there. But for spin 5/2 and higher, or spin greater than 2, actually this story contains the full Riemann tensor and most importantly wild tensor, and naively it looks like that there is no way to compensate these terms. This is true in the flat space, but not necessarily true in ADS. And the catch here is that actually one expands in powers of the Riemann tensor. The Riemann tensor can be considered to be a small expanding object around Minkowski space, but not necessarily about de Sitter. And that is the point. So, but before going to that point, I would like to emphasize that actually in the 80s there were very important papers by Swedish and Dutch groups showing that nevertheless they were able to construct some consistent cubic vertices for fields which contain higher derivatives. So, and the higher spin is, the more derivatives appear there. And just a very simple analysis shows that to make this, to make sense of it, one should have around some dimension full parameter just to make the action coherent to be dimensionless. So there is some raw parameter which is a kind of reminiscent maybe of Alpha prime from the string theory perspective, where also higher spin corrections appear, which on the other hand, in de Sitter, it can be related to the radius, ADS radius, and that actually will solve the problem. However, one can see that indeed the limit radius to infinity in this kind of expansion does not make much sense, and this is in agreement with the original no-go statements that in the flat space one cannot have consistent Hashman theories. So how it works in practice? Simply one should indeed expand in terms of the deviation of the Riemann from this cosmological term, which is small and de Sitter. So one covariantizes the original action, adds some higher derivative terms similar to those as reduced by Bengtson, Brink, and Beres, Vargas, Van Dam. And then one observes that one can add interaction terms proportional to this Riemann shifted tensor. And there is a finite number of terms for every given set of spins. And then one can analyze the variation using the fact that commutator of derivatives actually is proportional to a constant now, which is lambda squared, and which is not supposed to be small. So what happens that starting from the top order in derivatives, one computes variation. It will contain commutators, which means it will contain lambda squared. This term will decrease the number of derivatives, and the process goes on until the lowest order is precisely the variation compensates the original problematic term derived by argument data. Okay, so let me summarize. So the general properties are that higher spin interactions contain higher derivatives. There is non-elasticity in lambda, so that derivatives show up in this combination. And indeed, we can see now what does it mean that remaining geometry is not appropriate. The meaning is that if some of the higher spin fields will acquire a non-zero raking expectation value, then actually our equations will not second order anymore. They will be higher order equations in which propagation, for instance, is not determined by the second order part related to the metric tensor. So that is a dramatic change in the dynamics in that case. Okay, so there are different approaches to how to find this nonlinear deformation. It's not a simple problem. So basically there are two directions that I consider it, well, maybe three, there is also like one. But let me consider a Lorentz covariant approach. The one is just, let us start with the Kronzov fields. We, for instance, at the level of equations, we start with the free part of Kronzov equations, which is linear in phi. Then we can try to deform it by adding second order in phi terms, third order in phi terms, and so on and so forth, simultaneously deforming the transformation law for the Kronzov fields. Well, in this language, the additional terms may contain higher derivatives of the fields, and that is a very complicated problem, so that it has been solved in some lowest orders. But I mean, this way it's probably very hard to find the full form of this function g. In unfolded formulation, it's kind of similar. It's simpler in some sense, because it is formulated in terms of some modules of the Weil algebra. One can actually use some more algebraic tools to find corrections. And the point is that one should now expand in powers of C, which are zero forms. So we may have linear terms in C that we have seen already. We may look for quadratic terms in C and so on and so forth. And similar in this equation. And once we know that the compatibility condition implies gauge invariance, so gauge invariance results from this formulation. Okay. So this is how one can approach this problem. Still, it's very, very hard to find first corrections. Historically, they were found, like this one and this one. Well, it was clear that there should be a solution to this problem, but it was not clear how to reach it, actually. And let me now explain to you a trick that allows one to do it in some sense in all orders. So just before going to this, just summarizing is that in terms of unfolded formulation, we are talking about Hochschild homology of the Weil algebra. Hochschild homology appearance of infinity structure is actually not accidental. It's just expresses the fact that our symmetries are maximal. So from that perspective, we are talking about symmetries like GLV for some space V. So that's why associative algebras appear most naturally in this setup. Okay. So the idea is to reduce the complicated problem of finding all these corrections by a Hochschild homology of the Weil algebra to some simple problem of solving for the rank homology with respect to some additional variables. And this is what allows one to first to write down the general setup that allows to reproduce all nonlinear corrections, and at the same time explains how to go for generalization. Okay, so we have seen that our high-spin fields are given in terms of one form y and zero form c, depending on these variables y, which means that these connections are in the Weil algebra. Well, the trick is that we double the set of our variables, which are scalar variables y, in such a way that we will formulate equations that will remove this dependence on d at the end of the day, but at the nonlinear level, and will reproduce nonlinear corrections in the dizzy homology sector of the equations that I'm going to formulate in the next slide. So there are also so-called Klein operators, ky, k, and k bar. They square to 1, and then use some kind of, for instance, K, changes the sign of all left spinners. This is very important object that has many interpretations and actually will plays important role in the construction that actually is mapping finite dimensional modules to interdimensional modules of the twisted type that I have been considering. Okay.
Misha, sorry, on
Yes.
the right hand side you still have K capital. Is it a K or
K capital is just a pair of this K and K bar problem.
So they remain also inside Wij, for example, right?
Yes?
No, you wrote.
Oh, thank you.
Yeah.
Yeah, I forgot to erase this K capital. Thank you.
So K changes,
It's too much. Right. Thank
K
you.
changes the sign of the chiral and K bar the right.
Absolutely. Yeah. All right. So now I was talking about wild algebra, but so far gave no explicit formula for it. But in fact, a convenient way to describe wild algebra is by using the star product language of non-commutative geometry. So in this case, the non-commutative geometry actually works in the twistor space, in the spinor space of z and y variables. And here is the star product that describes wild algebra, which means function of oscillators, in the particular order, which is normal order in respect to z minus y and z plus y. And it also admits some Klein type operators that change chirality, that change the sign of left or right spinners. So let me just emphasize that for instance, z-independent sector, the star product reproduces the usual Mayal formula in this form. And that is very important formula for the theory because I want to make a comment that it is not local in y variables. It's actually contains all powers of derivatives on these variables. And let us remember that when we consider equations on higher spins, one of the equations contains d dy by, and this equation relates y dependence to x dependence through this equation. So the consequence is that if there is some non-locality in y variables, eventually it can be mapped to the non-locality in x variables. And this is what happens. So this is how this issue of non-locality shows up in this theory. So indeed, there are many, many derivatives in y variables, and that would mean that there are many derivatives in x variables. Good. So now the trick that I have announced, it's formulated like this one, can formulate equations. There are 5 equations for 3 types of field, W, B, and S. So the first 3, they contain space-time Durham differential here. And the other 2, given in red, they are free of any space-time derivatives. So they are formulated in the spinor space. This is, by the way, is actually related to this question of what is given by how equations are given by constraints. So the whole non-trivial part of the dynamics is given by these equations, which essentially look like a constraint from the perspective of space-time. So something very interesting happened by this reformulation because it turned out that the space-time of the story becomes dynamically trivial, at least locally, and the non-trivial part of the story is concentrated in the spinor space because this is the non-commutative curvature for the connection in the z-space, which has some specific form. And this is what is claimed is determines Hirschman equations and all nonlinear corrections to them. Well, these terms on the right-hand side, they are very special and have many interpretations. And one interpretation that, what determines these terms? Well, number one, the system should be consistent. Consistency means in particular that star product is associated, which means that S star commutator of this expression with S should be 0. Naively, it may look like it is not 0 because this K star kappa anti-commutes to S, changing the sign of left components. But in fact it is, because the only terms that are problematic are only proportional to dz. And because dz differentials are anti-commuting, it will contain dz to the third power, which is 0, because our spinors are two component. So that is why this system is consistent, and now it is important that indeed we are considering a four-dimensional system by using two-component spinors. So this is what makes this term distinguished. In particular, there are many other properties and interpretations. This is, in fact, kind of the Durham homology of the dz differential. And on the other hand, there is an interpretation for this term from the point of view of integrable system. I will explain this in a moment. So the corresponding commutation relations encode the structure which is known as Cherednik algebra in the simplest version, which is Z2. And that gives me possibility to extend this system to larger systems. So a couple of words about perturbative analysis. So how does it work? One starts with some vacuum for this system, which is given in particular by this formula. The P0S is the non-commutative flat connection. This is how the RAM is generated. And the W should be zero flat connection, which can be chosen to describe the system. Actually, this is the equation that describes ADS form. Then one can consider fluctuations. And the main observation is that, as I said, the commutator with S naught gives you the RAM with respect to dz. So the whole problem reduces to solving first those equations that contain dz, and whatever they are, this is always an equation like dz equals something built out of the lower order contributions through star product. And that can be solved explicitly at every order using some standard commodity formulas. For instance, this is the one that has been used for many years. But also one can use the other commodity formulas such that the result will be different by closed forms in z variables, which means just z-dependent or dz-exact terms. And this is one of the hot topics these days, to find which one is most appropriate from the locality perspective. Now, when one solves these equations, it's, as I said, it's just very explicit to solve. Then one plugs in the result in the remaining two equations which do not contain any S and therefore Z. So these are this equation and this. If you plug this result in here, then it turns out that the non-trivial part will be concentrated on the dz homology part of these equations. And that precisely reduces all nonlinear corrections to the original free massless field equations in all orders. So we somehow, using these additional variables, we managed to avoid complicated problem of solving for Hochschild homology.
Can I quickly ask you how the star product is defined?
Sorry?
How is the star product?
Star product is defined by this formula.
Okay.
All right. Now, so far, I was considering the highest gauge theory of the simplest possible type. That is, to some extent, is similar to string theory, but in some aspects is not similar at all. So let me discuss this and how to make a contact between them. So one important feature that I was about to emphasize is that the cosmological constant is not zero. All fields are massless. And these are all symmetric massless fields. Where in 4 dimensions there are no others. But in practice, this is more or less like first register projector. It's the spectrum in this model is far smaller than the spectrum of the whole string theory. Yes?
So for higher spin fields, is it necessary that they're symmetric, or it's a choice?
No, generally it's not necessary, but to have non-trivial mixed symmetry fields, as we call them, one should go to higher dimensions, for instance to 10 dimensions, then there is a room for them. In 4 dimensions there is just no room, they are all topological.
Oh, I meant symmetric, the fact that they're symmetric.
Yeah, I mean that there are no other massless fields in 4 dimensions. You may even have some non-symmetric indices, but as Poincare modules or antecedent modules, they're really the same. You may consider dual formulation, but nevertheless, the dynamically will be the same system. What I mean that in 3+1 there is no room for really mixed symmetry fields. But in higher dimensions, of course, there is a room, and that is the goal, that we should be able, actually that was what people were discussing for many, many years, how to formulate mixed symmetry fields to somehow make it possible to describe the system similar to string theory. So I'm trying to, in the remaining time, I will try to give some hints how that is probably possible to handle them.
Your spins are introducing.
Sorry?
Your spins are introducing?
Say it again.
Your spins are introduced? S equals 0, 1. I would expect 1/2.
Oh, no. Well, Fermats are around. It's just, I could read them as 0, 1/2 line, and so on and so forth. And there are different options for different spectra of spins. There are 3 two-parametric families for models with different types of spectra. This is just simple.
Okay.
Okay, so in string theory, we have massive higher string fields. And we have 1 equals 0. They should not be confused with statement to the ADS5 versus 5. Now I'm talking about cosmological constants, say, in ADS10. In ADS10, it's not clear how to introduce cosmological constants. Okay, so there are similarities and there are some differences. And of course, this actually was a long, old idea to try to make contact with these theories. And there were some proposals on the possible string-like extensions of higher spin symmetries. And I will explain you in the remaining few minutes a new proposal that has a good chance to work out of it. But let me start with the problem. Well, naively, what one should do, so we know that this is our original higher spin algebra, while algebra for oscillators. Why don't we let more oscillators be around? Just introducing more oscillators, trying to extend this construction to this case, but it doesn't work. It doesn't work for a rather trivial reason, which was realized immediately, is that we are talking about modules in terms of this unfolded machinery, modules of the simple algebras like anti-de Sitter. So these modules are given in terms of weights. For instance, from the conformal perspective, this is the weight of associated with the dilatation operator. And it is indeed goes appropriate so that the corresponding module has a room for stress tensor if we start with the original higher spin construction. But if we let more species of oscillators naively be around, then immediately what happens is that weight gets roughly multiplied by the number of oscillators. This is like increasing the weight and energy of the oscillators. And this weight does not correspond to stress tensor at the boundary. And it does not correspond to the massless field in the bulk, which means it's no more a theory of gravity in the bulk, no more conformal theory at the boundary. So it's just some nonsense. So this somehow should be avoided. And the resolution actually is very simple. One should deviate from the naive oscillator extension when we were just adding this color of N and M here, extending this way, that does not work. But it turns out that what does work is that we, in addition, introduce these idempotent elements associated to every species of oscillators, which essentially corresponds to the tensor product of the Weyl algebras in general. So if we do that, then actually in this construction, it is compatible with having stress tensor simply because these elements IN, different from different species, they can be defined to annihilate our vector space, all of them except for one. And that brings us back to the module that corresponds to Maslow's field, that describes Maslow's fields. So this is a simple construction. And now the remaining part is how to extend the nonlinear field equations. And I have to say a few words about Coxeter groups and Cherednik algebras, which is the construction underlying this story. So Coxeter group, let me just remind you, is generated by reflections with respect to a system of root vectors in a three-dimensional Euclidean vector space, so that the rank P Coxeter group. And the elementary reflection is just given by this simple formula, as I believe everybody knows. Well, but what is maybe less known is that every Coxeter group can be associated with what is called Cherednik deformation of the oscillator algebra. So if this term is absent, the second term, this is the standard oscillator algebra, which is the Weyl algebra. Then one can consider semi-direct product of the Weyl algebra and the group algebra of the Coxeter group that acts on the original oscillators in a standard way. So it just makes reflections with generators K when moved through Q generate reflection of the corresponding oscillator. So this is the definition of the algebra. Then the claim is that if we modify, deform this system to this one by adding terms containing this Klein operator, these are analogs of the Klein operator that I have introduced, then this system remains compatible with Jacobi. That is the key, one of the key issues. So one can check that Jacobi is still true. I mean, it's not very difficult to check. Not so much. One just should use definition, and basically it's almost trivial to see. But in practice, this has many consequences, and this is one of the actually hot topics these days that people are studying in math, the representation theory for Cherednik algebras, and there are some further extensions. The fact that Jacobi is satisfied is directly related to the consistency of Harrison equations, and therefore to gauge symmetries and so on and so forth. I will give you equations, final form of equations very soon. So this is what is called Cherednik algebra. There are a couple of coupling constants here, not couple, but as many as there are conjugates of classes of the corresponding Coxeter group, in the corresponding Coxeter group here. So there are different coupling constants in these systems. And by the way, this algebra is related to the Peabody Calogero model. This is, if you like, algebra of observables of the Calogero model. And that is how it was introduced in some other context. So this is very general story. So very briefly, the B2 and BP system is generated by reflections of individual x's and exchanging x's. And that is the system that I believe is related to string theory. Now the next step is that we should be able to consider frame extension of Cherednik system by introducing this additional idempotent elements. So that turns out in the end to be very simple. One should simply redefine the generators K by multiplying this by these idempotent operators. And that does not change so much, except that now they don't square to 1. So this is not a group algebra anymore, not even the great group algebra. So this, but still algebra. And that is the whole story for deforming Cherednik algebra. And now we can actually extend the step product to this case by plugging in these idempotent elements here. And that's actually all we need to extend the construction of higher-spin equations to a far larger class of theories associated with every Coxeter group. So all equations that had 0 on the right-hand side, they remain unchanged. So the only non-trivial equation was that containing x squared, which was the curvature for connections in spinor space. And here is how it looks like. So it's pretty much the same story as in the Cherny deformation when it introduces additional term, where this function f of b is a substitute for the couplings nu. So actually that's it. For the case of BP, Coxeter group, one has two coupling constants here. And what is interesting is that they have different meanings. So the second one, F2, appears for P2 or larger because it's responsible for the conjugacy class exchanging the axes in the original Euclidean space where the Coxeter group was defined. So in the P equal 1 case that was associated with the original higher-spin theory, there was no room for this additional term. And that is really crucial because that actually is something that leads to extension of the spectrum compatible with the full string pattern. Okay, so also one can add some matrix indices. There is infinite structure behind this, so one can consider fields value to many associative algebra, matrix algebras in particular. And also, to extend the system to what I call multi-particle theories that contain tensor products of the non-simple Coxeter groups. And most importantly, one can consider infinite product such that this product is also quotient over the symmetric group, so that this product is symmetric. The resulting algebra is really remarkable. It's actually is universal enveloping algebra of the original higher-spin algebra based on the Coxeter group, and as such it becomes Cope algebra. And this is what is conjectured to be related to the full-fledged string theory in the case of P equal 2. Well, higher structures. Higher structures means higher forms. So it's very easy to extend, actually necessary to extend this construction to higher forms simply by replacing one forms by forms of all odd degrees and zero forms by forms of all even degrees, and further modifying the interaction terms and allowing not necessarily linear terms in these line operators, but actually arbitrary functions of them that would contain some higher form contribution. This not only gives rise to higher forms in the spectrum, but also allows one to construct invariant functionals in this system as being associated with various central elements in the algebra, particularly the unit element. And that gives rise to the definition of some charges, like, for instance, asymptotic charges in the black hole case, and things like this. That has been checked, that they indeed reproduce appropriately the corresponding charges. So L is now a closed form that only depends on space-time coordinates. Okay, very briefly. Because of the appearance of these Klein operators, what happens is that if one considers some product of objects like this, moving K through this C will exchange arguments. So the result of that is that among operators, one will see operators with successively exchanged arguments, and the string of such operator is actually analogous to the string of single trace operators in ADS-CFT that show up in Anikel force original ADS-CFT correspondence. And there are others, of course, which can be considered as double trace or multi-trace operators. So this has to be compared to the original Hairston theory where only single particle trace operator were available. So the spectrum of operator extends a lot, enormously. So basically, it looks like that this spectrum is indeed, even for BP system, is appropriate for a description of the full-fledged Hairston-like string theory. Yeah. Well, I probably have to skip a whole same words. There are some interesting extension of this construction that one can actually extend the construction further by using some idempotence of the original wild algebras in wild variables. And that has interesting applications because this is basically how the brain-like objects appear in this construction. When one considers some modules which are smaller than a joint module or a twisted joint, this means that from a space-time perspective, they describe some dynamics on the smaller spaces. So this is very much like brains, except for these brains are not localized anywhere. So as long as Hairston theories are unbroken, this is more like projective picture where one identifies some particular directions rather than say that it is somewhere. Basically the relevant mathematical concept is the Delphine-Kirillov dimension, and that is what determines the space-time dimension of the corresponding objects in terms of modules. Okay, so there are two examples. One corresponds to vector-like models, and another, remarkably, corresponds to n=4 type systems in the B2 system, which is conjectured to be related to string theory. So I have no time to give you detail, but let me just emphasize that somehow the n=4 case is uniquely distinguished from that perspective. Because if n smaller than 4, then the system is inconsistent, there are some divergences. And if n is higher, then there is, then it's okay, but then no reduction to lower spins upon breaking Hairston theories can be achieved. But somehow n=4 is the only case which is distinguished and has a chance to be visible upon Hairston gauge symmetries are broken. That is a rather remarkable observation. Well, it remains to be seen, of course, how dynamically it can be realized. Let me come to conclusions. So, to conclude, this unfolded dynamics language is based on L infinity, and in Hairston case, basically on A infinity structures. So, it is appropriate for unifying somehow theories that live in space-time of different dimensions, so that's allowing to identify classes of telegraphically dual models. So Hairston gauge theories, they contain gravity as well as some infinite towers of fields of Hairston's, but also they include ordinary metric fields as well. And the main principle that was used to derive the models I was talking about, oops, probably time is over.
Еще бы это.
Oh, it looks like a computer. No, it's probably the problem with the computer.
It's battery?
Maybe. Okay, anyway, I'll send it. So it was the last slide. So that's so there is plenty of models that can be formulated that were not available so far, and at least there are as many as different Coxeter groups. So that is a new term that was not really explored so far in detail, so that remains to be explored. The most interesting story is if we do have enough room now in these models for Higgson, would it be possible to give masses to originally massless Hairston fields? If yes, and there is a good indication that it should be possible, there is a lot more states, then actually it should be some kind of string theory, because there were recently, by the way, some interesting papers indicating that if there is a massive high-string field, then the minimum option is just a string theory-like models with the inside amplitudes. So then, I mean, that would be a very interesting option to realize these higher symmetries in the spontaneously broken phase of string theory. Okay, and this is one of the hot topics and open questions that I was going to mention in the open questions part of the talk. So another hot topic which I think will be resolved, but still not quite resolved, is to analyze the issue of locality in more detail in the higher string theories, because indeed there are higher derivatives. So basically, from the L infinity perspective, this means that there should be some L infinity reduction of the L infinity that I was explaining to you, where the space of functions in which it is defined is more properly defined, is more restricted, and the corresponding machinery-like homotopy operators and so on and so forth have to be identified that would properly work within this class. So this is still an open question which is very interesting, and there is beautiful structure behind it which we partly see, but not full at the moment. Okay, I think I should stop here.
Are there any questions?
Yeah, so this unfolded equations for the function W that they considered, in your formulation was a Q-morphism from pi Cm to some Q manifold, right?
Yes.
So if we for a moment don't require that Q-morphism and consider slightly more general setup, so then you have a Q bundle over pi Cm. So then you can consider it as a section of a projection which plays a role of an anchor. And this can be interpreted geometrically as a section with an anchor as an analog of connection for transitive Lie algebroid, and the condition of this on these unfolded equations turns out to be flatness of this connection, exactly the condition of flatness of this connection. So this naturally brings the idea to consider this kind of field strength. Instead of considering just equation to be of flatness, just consider field strength and try to formulate some homogeneous equation in terms of field strength. So this partly was considered by Strobel and his collaborators, who were trying to build characteristic classes, not equations, but characteristic classes for this bundle, kind of generalized algebraic situation.
Well, may well be. It sounds interesting. In particular, what I was considering here was a kind of on-shell system, but in principle, this is curvature zero in some sense.
Yes.
But if you want to go off-shell, you should relax this, and that is probably one of the ways how one can think about this, how to do this. That is also important to have a kind of action for the system at the end of the day.
So the geometrical picture is a bundle, so Q manifold bundle over pi Tm. And this is an analog of Lie algebroid, so kind of non-linear Lie algebroid, transitive Lie algebroid. Because the anchor, the projection plays a role of an anchor, and the anchor in this case is surjective. So it is transitive, particular case of Lie algebroid, transitive Lie algebroid, but non-linear version.
Okay, thank you.
Didn't Grigoriev and others already give an AKC model description of these equations?
Well, people are discussing this kind of interpretation indeed.
That would be the action, or would be action.
Yeah, there are some papers on this.
And it would also.
Yeah, but there are papers by Persson, Dell, Nicolas Boulanger, and maybe someone else, precisely in this direction, to write down an action by adding one extra dimension. But the difficulty is that somehow they wrote some action that give rise to these equations, precisely these that I presented. But the problem is that actually this action is very far from the standard action. Even by this construction, they were not able to, as far as I know, to reproduce standard 5-box pipe, you know, for a scalar. So that's the action they derive is somehow very, very unusual. So that is all I know in this direction. Maxim wanted to?
Yeah, I wanted actually now to give two comments. First to the what Fyodor said. Indeed, the general situation, it's somehow just FDA is if you're interested in local geometry. Of course, if you want to describe if your base space is sophisticated and non-parallelizable manifold, then in general you may need this Q-bundle instead of, and then field the sections of these Q-bundles. And regarding the AKZ, of course, AKZ is some sort of, it's more or less the same thing, but AKZ contains negative degrees variables, and that's why it's like FDA with constraints, but also it automatically contains BRST extensions, so somehow it's like just better frameworks in some sense. And regarding the action, if you have your system in such an FDA form, then possible Lagrangian corresponds to graded presymplectic structure in this target space manifold. And this is somehow where you should look for Lagrangian. But of course it is slightly difficult for higher spins because it contains infinite amount of derivatives, it's unbounded order of derivatives, and that's why these presymplectic structures are not so clear how to work with them. But for simple systems like Einstein gravity, you can in 2 lines write down the symplectic structure for this Q manifold, which results in Cartan-Weil Lagrangian for gravity.
Other questions?
But, I mean, I don't think that there are any actions apart from those that I have been mentioning for this system. I mean, apart from for the nonlinear system, I think.
For the nonlinear, it's not. But what they wrote is not action. It's not compatible with Fraunhofer. It's an action, but it's not.
No, it's compatible with Fraunhofer in the sense that formulated solutions to those actions are equivalent to Fraunhofer, but somehow
Solutions, but not Lagrangians.
Yeah, that's what I mean.
There can be an
That's
equivalent
what I mean.
action, so the same
Yeah.
equation.
Yeah, that's what I mean. Yeah. The action do not reduce the normal Fraunhofer action. Right.
Further questions? If not, let's continue the discussion in the podcast.